So now that we have all this setup work done, let's take a look at exactly what a surface integral of vector fields actually are. Now, suppose S is this oriented parameterized surface with a unit normal vector n, and which obviously n determines the orientation. And consider a vector field F that is continuous on a region of R3 where the surface S is actually defined. Which represents, and F would represent the flow of, let's say, a fluid or transport of some type of substance. Given the surface S is smooth, we want to calculate the amount of flow across. And when we say across, we're talking about going actually through this surface. So again, we want to think of the surface as being an invisible membrane of some type, and we want to know how much passes through this membrane. And keep in mind that when we use the term membrane, we're actually using that as a figure of speech. It's like this invisible theoretical barrier that we're going through. This membrane does not have any mass. There's nothing to it to actually impede the flow through the membrane. It's more like a international boundary line in the Pacific Ocean somewhere. You can't go in and find a fence there. It doesn't exist. But there is a point where you actually pass from one area into the other where you've crossed that boundary. So it's that sort of an idea. So we have a couple different scenarios that we need to think about here now. If the vector field F and this normal vector n, these are actually, make sure you remember, these are vector fields and normal vectors here. They're aligned at the point P. So I have some point P on the surface. If the direction the field's flowing and the normal vector are aligned, so in other words, theta equals 0, then the component of F in the direction of n is going to be obviously F dot n. We're going to use a dot product here. But that's simply going to be the magnitude of F. So here's some point P, and here's my normal vector, and here's my vector field F. They're perfectly aligned. The angle between them is 0. Now we can see this from a dot product because F dot n is equal to the magnitude of F times the magnitude of n times cosine of theta. Well, remember, n is a unit normal vector, so this magnitude is just 1. Cosine of 0, if theta is 0, which we're talking about in this scenario, cosine of 0 is 1, so this really is nothing more than the magnitude of F. So in other words, all of F flows across the surface in the direction of that unit normal vector. Everything goes through in that direction. Now, if F and n are opposite in direction, the point P. So here I have my point P, and I'm going to say this is my unit normal vector. And let's just say that F flows in opposite in direction like this. Then the component of F in the direction of n is, well, once again, it's F dot n. Which in this case could be a negative magnitude of F, which means that F flows across the surface opposite in direction. So F flows opposite in direction of n. And again, we can get that from the dot product, because I'm going to have F dot n equals the magnitude of F times the magnitude of n times cosine of theta. So this is going to be the magnitude of F times 1, because it's a unit vector. Cosine of pi is a -1, so of course that gives me the negative of the magnitude of the vector field f. Now this last scenario we're going to talk about here is what if we're orthogonal. So what if f and n are orthogonal at the point P? So the angle is pi over 2. Well, if this is my unit normal vector, that's saying that f is perhaps like this, where this is a 90-degree angle. There's my orthogonal. I mean, it could be at any angle, long as this is 90 degrees. I mean, it could come over here or whatever, but the point is that they're actually orthogonal. So if they're orthogonal, then the direction or the component is going to be actually 0. And again, we can get that directly from the dot product. So f dot n equals the magnitude of f times the magnitude of n times cosine of theta, where here theta equals pi over 2. Cosine of pi over 2 is 0, so of course this is equal to 0. Now, if I have a situation, which is more common, I think, for 0 to be less than theta, which is less than pi over 2, so I'm going to have a vector field that has some other angle here, theta. The direction of the vector field at this point, I want to emphasize that point, has this angle theta. Then f dot n gives us a component of f flowing through the surface in the direction of n. That's really important. We're talking about in the direction of n. Yeah, if I have this angle theta, I mean, you could argue that all of f will flow through the surface, right? Because the surface doesn't stop it. It's a barrier with no mass to it. So all of f is going to flow through the surface. But what I'm interested in is the component in the direction of n. That's what I'm actually doing. So the flux integral, or the surface integral, when we think of it in terms of flux, which is very commonly referred to as the flux integral, really all it does is it simply adds up the components of f normal in the direction of the normal vector to the surface at all points on the surface. Just like the line integral through a vector field, we thought of it as adding up all of the work done by the vector field at each and every point along the path traveling through that vector field. It's the same sort of idea, only we're moving from a line, a curve in 3 space to a surface in 3 space.